When you look back at the earliest models of our cosmic neighborhood, the solar system was viewed as an incredibly cluttered and chaotic place. It is packed with millions of celestial bodies, drifting moons, icy comets, and endless swarms of asteroids moving through deep space. In 2006, the International Astronomical Union stepped in to establish order. They gathered to vote on a formal, strictly scientific definition for what actually constitutes a planet. To earn the title, a celestial body has to pass 3 physical tests. It must orbit the Sun, it must possess enough mass for its own gravity to pull it into a spherical shape, and its gravity must be dominant enough to clear its orbital path of any similarly sized debris. Pluto easily met the first 2 requirements, but because it sits in a crowded neighborhood of icy rocks, failing that final test meant it had to be reclassified into a separate category known as a dwarf planet. That ruling left us with an official census of 8 major planets. Together, these 8 bodies hold over 99% of all the non-stellar mass in our solar system. Yet, physically, they look almost nothing alike. If these 8 bodies accreted from the exact same primordial cloud 4.6 billion years ago, why did some compress into tiny, dense rocks, while others swelled into massive clouds of gas? Move one orbit outward to Venus, and a thick carbon dioxide atmosphere traps that solar heat. The resulting greenhouse effect crushes the surface under an atmospheric pressure 90 times greater than Earth's, pushing temperatures high enough to melt lead. Earth is the extreme outlier in this inner zone. It generated a strong global magnetic field that shielded its secondary, oxygen-rich atmosphere from solar wind, allowing liquid water to persist on its surface. Mars shows what happens when that magnetic shield fails. Roughly 4 billion years ago, the red planet lost its global magnetic field. Without it, the solar wind eroded the Martian atmosphere, leaving behind a freezing, arid desert. These 4 terrestrial planets were built from the same heavy materials. Their current realities, from toxic hothouses to frozen wastelands, are the result of their individual atmospheric and magnetic evolution. Leaving Mars, we enter the main asteroid belt. This band of millions of minor rocky bodies acts as a transition zone between the crowded inner system and the deep expanse beyond. This map illustrates a critical thermal boundary located roughly 5 astronomical units from the Sun. Out here, the temperature drops low enough for volatile compounds like water, ammonia, and methane to freeze completely solid. Astronomers call this the frost line. Once those volatile compounds survived as solid ice, the physical rules of planet building shifted. Suddenly, the outer solar system had an abundance of heavy building material that didn't exist closer to the Sun. With so much icy debris available, these outer cores grew incredibly massive. Their gravitational pull became strong enough to vacuum up primordial hydrogen and helium that had escaped the smaller inner planets. Jupiter grew into a behemoth with a mass 317 times that of Earth. Its scale generates a powerful magnetic field and drives swirling atmospheric storms, like the Great Red Spot, that are larger than our entire planet. Saturn followed a similar path, evolving a complex architecture dominated by an expansive ring system, which is maintained by the gravity of small shepherd moons. It even captured enough material to form Triton, a moon with its own dense atmosphere. These Jovian gas giants are essentially small, solid cores wrapped in massive layers of primordial gas. They are worlds defined by their gravitational dominance over the outer solar system. Pushing further into the darkness, between 18 and 30 astronomical units away, the Sun appears as little more than an intensely bright star. Solar energy out here is minimal. In this extreme isolation, we find Uranus. It orbits with a tilt of nearly 98 degrees, spinning essentially on its side and plunging its hemispheres into decades of uninterrupted winter. Neptune sits even further out, a dark sphere whipped by the fastest supersonic winds in the solar system. Its gravity is potent enough to have captured large, stray objects, pulling icy moons like Triton into permanent orbit. The ice giants show us how the thermal gradient behaves at the far edge of the planetary system. Out here, much of the solar nebula's original history is locked in a permanent deep freeze. Past Neptune lies the Kuiper Belt,
a vast field of frozen remnants stretching out until we hit the heliopods at 120 astronomical units. That boundary marks where the solar wind stops and interstellar space begins. Stepping back to view this entire mechanism, it is worth noting that every one of these diverse worlds originated from the same primordial cloud 4.6 billion years ago. Their current states are the result of physical variables: distance from the sun, their gravitational mass, and a magnetic field.
When you place our living oasis against a backdrop of irradiated rocky deserts and violent gas giants, you see exactly how precarious our position is. Earth exists where the physics allowed it to, and nowhere else. Look at it quickly, and you might think you're looking at our moon. For decades, that was the scientific consensus on Mercury. Sitting so close to the sun, it was largely dismissed as a dead, sun-baked cinder, a dry rock where nothing much has happened for billions of years. That assumption held until 2011, when NASA's Messenger spacecraft finally slipped into orbit around the planet to take a closer look. As the spacecraft began its 4-year orbital mission, the raw measurements arriving at mission control looked nothing like the expected readings from a dead, scorched rock. Instruments detected massive deposits of ice on a world hot enough to melt lead. They also found volatile chemicals, elements like sulfur and potassium, which evaporate so easily they should have been boiled off into the vacuum of space billions of years ago. Mercury is a dynamic, actively shrinking world. It harbors fire and ice in a combination that forces us to reconsider the entire history of our solar system. Orbiting at roughly a third of the distance between the Earth and the Sun, Mercury is a planetary oven. At high noon, surface temperatures soar to 800 degrees Fahrenheit. Yet, hiding at the North and South poles are massive deposits of frozen water. This diagram shows how sunlight interacts with Mercury's polar terrain. Earth tilts on its axis, giving us shifting seasons. Mercury has virtually zero axial tilt. That means at the poles, sunlight only grazes horizontally across the landscape. If you plunge down into the deep craters near those poles, the sun's rays never reach the bottom. These pockets of permanent shadow create deep freezes where temperatures sit at -300 degrees, trapping ice for billions of years. Moving from the surface to the interior reveals a second paradox. This graphic shows a cross-section of Mercury's internal structure. Because it's the smallest planet, it should have cooled and completely solidified eons ago. Instead, it harbors a massive, semi-molten iron core that takes up over 60% of the planet's total volume, leaving only a thin shell of rock around it. Because that massive iron core is still liquid and churning, it acts like a dynamo, generating an active global magnetic field that constantly wrestles with harsh solar winds. As charged particles from the sun slam into the surface, they knock atoms of sodium and calcium off the rocks and out into space, creating a glowing, comet-like tail that stretches for 2 million kilometers behind the planet. Mercury is magnetically alive, continuously venting its own thin atmosphere into the void. This oversized core creates a challenge known as the Mercury problem. There was no clear explanation for why a planet would form with so much metal and so little rock. For years, the leading hypothesis was a catastrophic head-on collision. Early in the solar system's history, a massive impactor supposedly struck Mercury dead-on, obliterating its thick, rocky mantle and leaving only the dense iron heart behind. But MESSENGER's chemical analysis challenged that hypothesis. The probe detected high concentrations of volatile elements scattered across the surface, along with widespread evidence of ancient, explosive volcanic ash. If a direct head-on impact had stripped away the planet's crust, the resulting friction and heat would have instantly vaporized those delicate chemicals into space. They survived, which means that catastrophic heat never happened. This animated model demonstrates a newer hypothesis, a grazing collision. Instead of a direct hit, a similarly sized body struck early Mercury at a shallow angle. This hit-and-run sheared off the outer rocky layers and carried them away, leaving the core intact without generating enough heat to boil off the volatile elements. Mercury appears to be the surviving remnant of a cosmic hit-and-run, preserving the exact chemical fingerprints of its violent birth. Understanding how it formed is only part of the challenge, because existing on Mercury means dealing with a bizarre physical reality. The planet's rotation and its orbit are locked in a 3-to-2 resonance. It spins on its axis exactly 3 times for every 2 full orbits around the Sun. Because of this, a single solar day from sunrise to sunrise takes 176 Earth days to complete. If you stood on the surface, you would experience 2 entire Mercurian years before the Sun rose again. That surface is littered with strange, bright depressions known as hollows. With no atmosphere, there is no wind or rain to erode the landscape, meaning some other unknown process is actively eating away at the rock. Deep underground, the massive iron core is slowly cooling. As the metal loses heat, it contracts, causing the entire planet to physically shrink. The crust crumples in response, enlusting up massive cliff-like scarps that run for hundreds of miles. Decoding these unearthly extremes provides the context needed to map the evolution of Earth and the entire inner solar system. To solve the remaining contradictions, the European and Japanese space agencies launched a joint mission known as Bepi-Colombo. Catching Mercury is notoriously difficult. Flying inward toward the Sun means a spacecraft accelerates continuously as it falls into the star's massive gravity well. To avoid overshooting the planet entirely, the probe has to constantly hit the brakes. This orbital map tracks Bepi-Colombo's complex trajectory. Instead of a straight line, it utilizes multiple gravity assist flybys past Earth, Venus, and Mercury itself. Each pass deliberately bleeds off kinetic energy, allowing the craft to slowly and safely fall into a stable orbit. Once it arrives, the mission will split into 2 distinct orbiters, mapping the surface and measuring the magnetosphere simultaneously. Humanity is finally poised to catch the fastest, most extreme planet in our solar system, revealing the mechanics of a world we are only beginning to understand. Look up just after sunset, and the brightest natural point of light is Venus. For centuries, humanity looked at that brilliant glow and tied it to the classical Roman goddess of love, beauty, and desire. Early astronomers assumed this physical beauty matched a planetary reality. Venus has a radius of 6,052 kilometers, almost identical to Earth's. It has roughly the same mass, and it orbits in our immediate neighborhood. The natural assumption was that Venus was Earth's twin, likely hiding lush, temperate environments beneath its bright clouds. Then we sent space probes there. In the 1960s and 70s, Soviet and American landers punched through the clouds and found a runaway greenhouse environment. The atmosphere is 96% carbon dioxide, creating a layer of supercritical fluid near the surface, where temperatures reach 870 degrees Fahrenheit, enough to melt lead. The atmospheric pressure at the surface is 92 times greater than what we experience at sea level on Earth. Standing on the surface of Venus would feel like being trapped 900 meters underwater. The data was conclusive. The planet named for beauty is a toxic, runaway greenhouse hellscape, a realization that forced us to reconsider our relationship with our closest neighbor. With environmental conditions this hostile, a new consensus took hold. Venus was a static, dead rock, locked in an eternal, lifeless bake. Because of this conclusion, humanity largely walked away. The grand ambitions of planetary exploration pivoted outward, shifting almost entirely to the cold, quiet deserts of Mars. But over the last few years, a slow trickle of strange, anomalous data has surfaced, sparking intense debate among planetary scientists. The numbers suggest we gave up on Venus way too soon. To understand why scientists are now rushing back to the second planet, we have to look past the blinding glare of its outer clouds and physically descend through its thick, obscuring atmospheric layers. Down there, hiding underneath the toxic haze, are active, dynamic systems that have been operating in secret for billions of years. This animated cross-section shows Venus's atmospheric layers. Dropping to 48 to 60 kilometers, you hit a temperate cloud deck where temperature and pressure match Earth's surface. But the chemistry is hostile. These clouds are concentrated sulfuric acid, a fiercely aggressive solvent. Yet in 2020, researchers detected the chemical signature of a gas called phosphine inside this exact cloud deck. On Earth, phosphine is heavily associated with the biological processes of living microbes, making it a compelling potential biosignature. This detection begged a massive chemical question. Could anything actually survive in that acid? To find out, a 2024 study dropped 20 biogenic amino acids,
the structural building blocks of life, directly into concentrated sulfuric acid at Venus-like temperatures. After 4 weeks of incubation, 19 of those amino acids remained stable. Their central structural backbones stayed completely intact, unreactive, and undestroyed. The molecules required for life can persist inside the solar system's most destructive chemical environment. An extremophile biochemistry floating high above the Venusian surface is a mathematical and chemical possibility. The chemistry in the atmosphere is the visible output of geological processes occurring on the surface. Dropping to the dark, high-pressure ground requires specialized tools because the permanent cloud cover forces us to map the terrain using radar. Back in 1991, NASA's Magellan spacecraft did exactly that, bouncing radar waves off the planet's surface to construct a global map. This 3D radar map reveals Mont Mons, a massive shield volcano long considered a dormant relic. However, a 2023 reanalysis of this original Magellan data revealed a specific volcanic vent had changed shape, expanding and overflowing with a fresh lava flow over an 8-month window. This physical eruption explains the presence of chemicals in the clouds above. Magma deep within the planet is rich in a mineral called phosphide. When an active volcano erupts, it blasts that phosphide high into the atmosphere, where it reacts with sulfuric acid to create phosphine. The data sets align. Venus is geologically active right now, and its surface eruptions directly drive the chemical environment in its sky. Active geology and resilient organic chemistry. The data has shifted our view of Venus from a frozen relic to a world of active, interconnected systems. This realization has triggered a space exploration renaissance. By the early 2030s, an entire armada of new missions will arrive at our sister planet. NASA's upcoming Da Vinci mission will drop a heavily shielded spherical probe straight down through the exact atmospheric layers and toxic clouds we just examined, sampling the chemistry meter by meter. From above, a broader international fleet, including NASA's Veritas and the European Space Agency's Envision, will orbit the planet to remap the active volcanic surface with modern, high-resolution radar. This upcoming fleet represents a transition into the physical interior of a dynamic planetary system. 2 planets built from the same materials at the same time, orbiting right next to each other. One became a habitable oasis, the other became a toxic pressure cooker. Probing these hostile environments addresses a fundamental question of planetary survival. Uncovering exactly how Venus suffocated explains why Earth flourished, providing the data we need to ensure our own world avoids the same fate. Earth has spent 4.5 billion years sitting exactly 1 astronomical unit from the Sun. At this precise distance, the planet maintains a temperate climate and holds vast reserves of liquid water on its surface. But look 1 planet further out. Mars sits within this same habitable zone, yet it exists as a frozen, irradiated desert where the atmosphere is barely a fraction of a percent as dense as our own. Look 1 planet inward and you find Venus. The surface of this planet bakes at 748 Kelvin under a crushing atmosphere of carbon dioxide and thick clouds of sulfuric acid. All 3 of these planets formed at roughly the same time, from the exact same primordial dust and gas, in the exact same neighborhood of the solar system. Yet 2 are completely dead, while the 3rd teems with life. What exactly keeps our world alive? Earth does not stay comfortable by magic. It relies on a set of massive, hidden mechanical engines continuously working to maintain the environment. To understand how they keep Earth alive, we have to look at how those exact systems failed on Mars and Venus. Mars actually holds the physical scars of ancient riverbeds and flowing water. It lost that liquid water because it lost its magnetic shield. Without that defense, high-energy particles from the solar wind systematically stripped away the Martian atmosphere over billions of years. Earth counters this deep inside. Beneath the crust lies the core, solid iron surrounded by molten metal. As Earth rotates, this liquid layer churns, acting as a geodynamo. It generates a massive magnetic field projecting into space, deflecting the solar wind. We often think of a cooling planet as a safer planet, but a calm interior is a dead interior. The surface remains habitable specifically because the deep core remains violently hot and active. Venus suffered a different type of systemic failure. Its atmosphere slowly became 96% carbon dioxide, trapping incoming solar heat. This created a runaway greenhouse effect that permanently oiled away any chance of liquid water. Earth avoids this fate through the carbonate-silicate cycle. Carbon dioxide is drawn out of the air by rain, weathering rocks and settling on the ocean floor. Through plate tectonics, this trapped carbon is subducted deep into the mantle, safely removing it. Shifting tectonic plates cause earthquakes and eruptions, but they act as a necessary atmospheric pressure valve. Without a moving crust to recycle carbon, we would choke under a toxic sky. Above that shifting crust, remaining gases settle into distinct layers, stretching from the troposphere to the exosphere. This stratification distributes global heat, absorbs harmful ultraviolet radiation, and burns up incoming meteors. Even with all these systems running, Earth's climate would swing wildly without external stabilization. We orbit with a single, unusually large moon. Its gravitational pull locks Earth's axial tilt at roughly 23.4 degrees, preventing extreme orbital wobbles and chaotic climate shifts. The molten core, the tectonic crust, the layered atmosphere, and the orbital tether of the moon must all operate in constant, simultaneous harmony. But these biological and geological engines run on a finite amount of fuel. If we look deep enough into the future, astrophysical models can predict exactly when those engines will stall. The first major failure point arrives in about 1 billion years. The sun's luminosity will increase by 10%. That extra solar radiation will heat the Earth enough to cause the oceans to boil, triggering the exact runaway greenhouse effect that sterilized Venus. If anything survives that, the geological clock runs out in 2 to 3 billion years. Earth's interior will cool enough for the molten outer core to solidify, shutting down the geodynamo. With the magnetic shield gone, the solar wind will peel away whatever remains of our atmosphere, repeating the fate of Mars. Finally, in roughly 5 billion years, the Sun will exhaust its core hydrogen. It will expand into a red giant, swelling outward until it entirely engulfs and vaporizes the Earth. The mechanical conditions that make life possible are highly specific and inherently temporary. The safe operating space we currently enjoy is a fleeting, beautiful prime in deep time. Mars is the only planet in the known universe inhabited entirely by robots. Right now, a fleet of dozens of orbiters, landers, and rovers are actively patrolling its surface and skies. These machines operate in a punishing environment. The average surface temperature is -85 degrees Fahrenheit. The atmosphere is 95% carbon dioxide, and global toxic dust storms regularly sweep across the rocky terrain. Billions of dollars are being spent to explore an irradiated, freezing desert that, from a distance, appears completely dead. We are there because our earliest assumptions about the red planet were wrong. Our initial telescopic views suggested a boring, lifeless rock, but the moment we sent cameras into orbit, that assumption was shattered. In 1971, the Mariner 9 spacecraft arrived to map the planet. It was the first probe to successfully orbit another world, and it sent back images of a massive geological anomaly. This high-altitude orbital photograph reveals the complex, layered structures of Valles Marineris. Alongside this massive canyon system, probes discovered giant dried-up river deltas and ancient lake beds carved into the crust. The deep, eroded channels found in this specific canyon system require massive amounts of liquid water to form. These structures are the physical proof that Mars was once a warm, wet world. Mars is a planetary crime scene. If a warm climate and flowing water existed billions of years ago, we need to know where it went and what biological traces it left behind in the soil. To solve this mystery, NASA developed a singular, overarching strategy: follow the water. That strategy led to missions like MAVEN. Instead of looking at the ground, MAVEN was deployed as an atmospheric detective to study the sky and understand how the Martian environment evolved. Earth generates a global magnetic field that deflects solar winds. Mars lacks this protective shield. Without a magnetic field, the Martian atmosphere was completely exposed. Over billions of years, high-energy particles from the sun stripped away the thick gases that once kept the planet warm. Atmospheric pressure acts like a blanket that stabilizes liquid water. Once that blanket was lost, the oceans and rivers were forced to either freeze deep into the dirt or evaporate directly into space. With the atmospheric timeline established, the investigation shifted back to the surface. Advanced rovers act as mechanical detectives, driving through the ancient, dried riverbeds to examine the rocks left behind. Early missions proved we could land a vehicle on another planet for targeted sampling, analyzing specific rocks to see what they were made of. Modern rovers have since uncovered concrete evidence of liquid salty water seeping through the crust, and they've even detected organic molecules, the chemical building blocks of biology. But these machines have a physical limit. Even with state-of-the-art onboard chemistry labs, a rover cannot definitively identify a fossilized microbe on its own. Confirming the existence of biological chemistry requires electron microscopes and mass spectrometers. We need the massive, power-hungry laboratories that can only be found on Earth. The next stage of the investigation involves the Mars Sample Return Campaign and Rosalind Franklin rover. These missions are designed to provide the definitive physical evidence we've been searching for since the 1970s. This is a Martian sample collection tube. Perseverance is actively drilling into the surface, caching pristine rock and dust inside these sealed cylinders. The plan? Send a future spacecraft to Mars, collect the tubes, and fly them back to Earth. Opening these samples in an Earth-based laboratory will tell us about Martian history, but it also provides a natural laboratory for our own planet. It allows us to study how a habitable world loses its climate, providing a direct lens into Earth's past and future. The search for ancient life is now running alongside a more immediate goal: human exploration. Future survival relies on in situ resource utilization, the ability to live off the land. We are testing the limits of this concept through the MOXIE experiment. MOXIE generates breathable oxygen out of thin air. It pulls in Martian carbon dioxide, splits the molecules with heat, and outputs pure oxygen. This solves massive weight limits for deep space travel, removing the need to launch every oxygen tank. The robotic presence on Mars is building a bridge to the future. Our machines explore the ancient dead, so that one day soon, the living can follow. When we observe Jupiter through a telescope, the eye naturally settles on the Great Red Spot and the thick bands of swirling gas. It looks like a massive, isolated sphere of weather suspended quietly in the dark. But decades of deep space probes have revealed a very different reality. Jupiter is a violently active, fully functioning mini-solar system. It governs a vast, chaotic neighborhood. It sustains traps of intense radiation. It grinds down orbiting rock to maintain decaying rings of dust and harbors oceans beneath solid ice. All of this diverse activity raises a specific mechanical question. How does the immense power radiating from one planet's core physically control an entire planetary system? To understand how Jupiter works, we have to look past the visible cloud tops and track the physical engine driving its immediate neighborhood from the inside out. That engine sits at the very center of the planet. Jupiter's interior is packed with metallic hydrogen. As the planet rotates, this liquid metal churns like a dynamo, generating an immense magnetic field. This field balloons 3 million miles toward the Sun and trails 600 million miles behind, engulfing the largest moon's orbits. As the planet spins, this massive field sweeps up charged particles, accelerating them to extreme speeds, creating swarms of highly energized ions and electrons. This invisible radiation trap constitutes the violent weather of the inner Jovian system. Any object orbiting near the planet must survive a constant degrading bombardment. That violent environment extends outward, shaping a feature usually associated with Saturn, a ring system. Unlike Saturn's bright bands of ice, Jupiter's rings are faint and made entirely of dark reddish dust. This dust has a violent origin. High-speed micrometeoroids from deep space constantly smash into Jupiter's 4 small inner moons, forcefully ejecting clouds of rock and dirt into the surrounding vacuum. Once ejected, the dust is caught by Jupiter's magnetic field and the drag of solar radiation. These forces physically pull the chaotic debris clouds, flattening them into the distinct main, halo, and gossamer rings that circle the planet's equator. Because this material is constantly destroyed by collisions or dragged down into Jupiter's atmosphere, the rings are remarkably young, likely less than 1 million years old. They require a constant supply of fresh impacts to survive. Jupiter's rings are an active, real-time recycling grinder, continually fed by celestial collisions and shaped by the planet's magnetic pole. Further out, this grinder gives way to a collection of distinct worlds, the Galilean moons. Jupiter's influence yields wildly different results here, ranging from the heavily cratered surface of Callisto to the active volcanoes of Io. Then there is Europa. In the late 1990s, probes deployed directly from the Space Shuttle gathered data, proving that Europa's smooth, fractured ice shell hides a massive liquid ocean, containing more water than all of Earth combined. Liquid water requires heat, provided by tidal forces. As Europa orbits, Jupiter's gravity stretches and squeezes the moon, generating friction. This creates tremendous pressure beneath the crust, shooting plumes of water vapor 125 miles into space through deep cracks. Jupiter's immense, brutal gravity is the exact mechanism that prevents Europa from freezing solid. The pull of the gas giant actively kneads a frozen rock into a geologically active world. A core generating a radiation trap, micrometeorites grinding moons into dust, gravity crushing a frozen crust. All these elements operate together as a highly active, interconnected machine. Because of this churning Jovian engine, the core ingredients for life, liquid water, chemical nutrients, and an energy source, are currently mixing beneath Europa's ice. The investigation of this environment is ongoing. Spacecraft like NASA's Europa Clipper and the European Space Agency's JUICE mission are en route right now to determine if these subsurface oceans contain the right conditions for biology. The mystery that Galileo started over 400 years ago is entering its most important chapter. We are on the verge of discovering if the chaos of the Jovian machine has forged a second home for life in our solar system.
For centuries, when humanity looked up at Saturn, we saw a masterpiece perfectly frozen in time. Ever since Galileo first spotted the planet through a telescope in 1610, we assumed these iconic rings were a permanent fixture of our solar system. But 13 years of data collected by the Cassini spacecraft has upended that understanding. Saturn's rings are actively dying. They are draining into the planet like a conveyor belt, and in less than 100 million years, they could vanish entirely. To truly understand Saturn, we have to account for its constant motion, a hyperactive cycle of violent creation and destruction. The scale of this system is difficult to comprehend. You could fit 750 Earths inside Saturn's volume, yet its density is so low that if you could find a body of water large enough, the entire planet would float. There is no solid surface to stand on.
It is a gas giant composed almost completely of a hydrogen and helium mixture that simply gets hotter and denser the deeper you go. The smooth butterscotch bands we see from space are actually the result of extreme weather, driven by winds whipping around the equator at 1,100 miles per hour. At the planet's North Pole, this atmospheric chaos organizes into a bizarre anomaly, a permanent hexagon-shaped jet stream churning in continuous motion. Beneath its peaceful exterior lies a hostile, churning fluid engine that dictates the gravitational rules for everything trapped in its orbit. Those gravitational rules apply directly to the rings. From a distance, they look like solid disks, but they are actually billions of independent chunks of nearly pure water ice. These ice particles vary wildly in size, ranging from microscopic grains of sand to floating boulders the size of a house. As these pieces bump and grind in orbit, they create viscous interactions, friction pushing ring material outward and inward simultaneously, like a conveyor belt. At the inner edge, material loses its footing, constantly raining down and burning up. Simultaneously, at the outer edge, icy material safely clumps together, forming tiny new moonlets. The rings exist as a temporary state of transition, a massive, active cycle of cosmic recycling. This recycling process is regulated by a massive collection of natural satellites. With 293 confirmed moons, Saturn hosts the largest planetary system in our stellar neighborhood. Some of the inner moons act as orbital snowplows. Their gravity physically sculpts the ice, carving out gaps and leaving turbulent, rippling wakes as they plow through the rings. Further out, the Cassini mission made one of its most startling discoveries, a moon named Enceladus, completely encased in a deep layer of bright white snow. Beneath that icy crust, Enceladus hides a global ocean, firing massive geysers of water and organic compounds straight into space. That ejected material physically supplies Saturn's massive outer E-ring. Then there is Titan, Saturn's largest moon. It boasts a thick, hazy atmosphere, clouds that rain liquid methane, and vast hydrocarbon lakes pooled on its surface. These moons function as the mechanical heart of the system, physically driving the evolution of the rings and churning out the chemical complexity found across the neighborhood. The planet, the rings, and the moons are locked in a continuous gravitational dance, constantly exchanging and consuming material. The way these ring particles collide, spread, and clump into moonlets provides a real-time analog for the protoplanetary disks of the early solar system. By watching this system in flux, we can observe the same gravitational physics that built the planets billions of years ago. But the most compelling discoveries are astrobiological. The organic compounds shooting out of Enceladus and the liquid seas on Titan represent the exact chemical building blocks necessary for biology. With their active geology and hidden liquid oceans, these moons currently stand as our most promising targets for finding extraterrestrial life. We are already preparing to go back. NASA's upcoming Dragonfly mission will send a robotic rotorcraft to fly directly through Titan's hazy skies and explore those alien lakes up close. The breathtaking rings that define Saturn are steadily fading into history. Yet the dynamic, chaotic system that is destroying them might finally provide the evidence we need to answer whether life can take hold in the cold reaches of the outer solar system.
In 1986, humanity got its first and only close-up look at Uranus when the Voyager 2 spacecraft flew past. The images it beamed back showed a featureless, pale blue sphere. For decades, that flyby cemented its reputation as a quiet, inactive, and relatively boring world. Modern observations using advanced infrared telescopes have shifted that perspective. Beneath the pale exterior lies a highly dynamic atmosphere that contradicts early models of how this world was expected to behave. Uranus stands out as the solar system's most prominent outlier. While it follows the same laws of gravity and motion as its neighbors, its orientation is a stark departure from the typical planetary blueprint. Most planets spin relatively upright, like tops spinning on a table. Venus rotates in reverse, but Uranus takes it a step further. Its equator is tilted at nearly a 90-degree angle to its orbit, and it rotates backward. That 97.77-degree tilt forces the entire planet to operate perpendicularly to the rest of the solar system. This sideways posture creates a unique atmospheric and orbital environment found nowhere else in our neighborhood. About 4.5 billion years ago, a massive protoplanet, likely the size of Earth, slammed into Uranus. The kinetic energy of that impact knocked the ice giant completely off its vertical axis. Because of that strike, Uranus doesn't spin like a standard top as it circles the sun. Instead, it rolls along its orbital path like a ball. This horizontal orientation distorts how the planet receives sunlight. For a full quarter of its massive orbit, one pole points directly at the sun. Since it takes Uranus 84 Earth years to complete a trip around the sun, that translates to 42 years of continuous sunlight on one pole, while the opposite hemisphere is trapped in 42 years of dark winter. These are the most prolonged and intense seasonal shifts of any planet we know. The temperature differences between decades of continuous light and dark drive the planet's atmospheric dynamics in ways we are only beginning to measure. Understanding these physics requires looking beneath the clouds. Uranus is an ice giant, meaning its mantle isn't made of solid ice, but rather a highly pressurized, electrically conductive fluid ocean of water, ammonia, and methane. Earth's magnetic field is generated by a dynamo effect in its molten iron core. On Uranus, the magnetic field is generated inside that swirling, electrically charged fluid mantle. Because it is generated in the mantle, the planet's magnetic field isn't anchored to its center. The heart of the field is actually shifted away from the planet's physical core by a full third of its radius. It is also crooked. The magnetic axis is tilted 59 degrees away from the planet's already sideways rotational axis. When you combine a lopsided magnetic tilt with a planet that rolls on its side, the rotation twists the magnetic field lines. It creates a massive corkscrew shape, trailing millions of miles into space.
This asymmetrical magnetic field creates non-uniform forces that challenge our understanding of how magnetospheres interact with solar wind. The planet acts as the anchor for an entire sideways ecosystem, holding 13 rings and 28 known moons in its tilted gravity well. Recent spectral analysis shows that the new ring is composed of typical red, rocky debris, the leftover material from ancient collisions. The neighboring Mu ring, however, is a rare, striking blue. It consists of microscopic water ice particles continuously knocked off the surface of a tiny embedded moon named Mab by micrometeorite impacts. The larger moons are also volatile, particularly Miranda. Its surface looks like it was shattered into pieces and reformed several times over. Miranda is home to Verona Rupes, the tallest known continuous vertical cliff in the solar system. It features a sheer drop of 20 kilometers. Because Miranda's gravity is weak, an object dropping off the edge of Verona Rupes wouldn't plummet. It would fall 12 minutes before hitting bottom. From dust rings to shattered moons, every part of this system is governed by the extreme tilts and ancient collisions that define the planet. Decoding these oddities is crucial for a reason that extends far beyond our own solar system. As telescopes catalog thousands of worlds orbiting distant stars, a pattern has emerged. This chart categorizes the exoplanets we've discovered so far. More than 30% of all known exoplanets are ice giants, roughly the same size and composition as Uranus. This creates a significant gap in our knowledge. If we cannot explain the internal chemistry and magnetic behavior of the ice giant in our own system, we lack the framework to understand billions of similar worlds across the galaxy. This is why the planetary science community recently designated the Uranus orbiter and probe as a top mission priority for the next decade. Returning to Uranus to study its atmosphere directly provides the data necessary to model the behavior of the most common type of planet in the cosmos. Up until the mid-19th century, finding a new planet meant staring through a telescope until you spotted a speck of light moving against the background stars. Finding the eighth planet required a different tool: calculus. This diagram shows Uranus's orbit in the 1840s. The path follows standard Newtonian physics, but observations revealed a persistent wobble, a physical deviation from the math. Astronomers hypothesized an unseen planet further out. Adding this mass to our model perfectly corrects Uranus's orbital path. Galileo Galilei actually recorded this exact body in his notebooks back in 1612. Because it moves so slowly across the sky, he cataloged it as a fixed star and missed the true nature of what he saw. By the 1840s, astronomy was shifting from a practice of cataloging points of light into a rigorous discipline of deductive physics. If the established laws of gravity were correct, a massive hidden world had to exist. French astronomer Urbain Le Verrier set out to find this missing mass. Working entirely on paper, he calculated the precise location required to cause the anomalies in Uranus's orbit. At the exact same time in England, astronomer John Couch Adams was performing nearly identical calculations. Both men were relying on theoretical math to pinpoint a world neither of them could actually see. On the night of September 23, 1846, German astronomer Johann Galle received a letter containing Le Verrier's coordinates. Galle pointed his telescope at the Berlin Observatory exactly where the math dictated and found the new planet within 1 degree of the predicted spot. We had located the eighth planet, Neptune, but its physical nature remained a mystery. It took a flyby from the Voyager 2 spacecraft in 1989 to finally reveal what this world actually looked like. The certainty of those early mathematical equations gave way to a physical world defined by extreme anomalous behavior. Neptune orbits roughly 4.5 billion kilometers from the Sun. At 30 times the distance between the Earth and our star, logic suggests a cold, dead, and entirely frozen sphere. Looking at this cross-section of Neptune, you can see a massive temperature gradient. The outer atmosphere sits at a freezing -220 degrees Celsius. But as we move toward the core, the temperature spikes to nearly 8,000 degrees, hotter than the surface of the Sun. Zooming into the middle layer here, we find the mantle, Under pressures 8 million times higher than Earth's atmosphere, materials like water, ammonia, and methane melt into a giant boiling fluid bath. This intense internal heat radiates outward, colliding with the freezing upper atmosphere. That temperature differential creates a thermodynamic engine that drives the solar system's fastest winds, reaching supersonic speeds up to 2,100 kilometers per hour. These winds whip up massive, transient storm systems.
Voyager 2 observed an anticyclone large enough to swallow the entire Earth, dubbed the Great Dark Spot. Just 5 years later, the Hubble Space Telescope looked for it, and the storm had vanished, replaced by new ones in the northern hemisphere. The violence of Neptune's atmosphere proves that planetary energy doesn't rely entirely on radiation from a host star. A planet can generate catastrophic weather purely from its own internal heat. The extreme conditions aren't limited to the planet's surface. Moving outward into the vacuum of space, Neptune hosts a complex ring system. This top-down view shows Neptune's outermost structure, the Adam's ring. According to standard orbital mechanics, the icy debris here should spread out evenly. Instead, the material clumps into 4 distinct dense arcs, named Liberty, Equality, Fraternity, and Courage. The cause of this clustering is a tiny shepherd moon named Galatea sitting just inside the ring. As it orbits, it exerts a precise gravitational pull, locking these dusty clumps into stable positions and keeping them from dispersing. The structure of these arcs shows how localized, invisible gravitational forces dictate the architecture of planetary material, holding millions of icy particles in an intricate balance. Galatea is just one piece of a larger satellite system. Of the 14 known moons around Neptune, a single body named Triton accounts for 99.5% of all the orbiting mass. This tracking visual highlights Triton's most defining anomaly. While Neptune rotates in one direction, Triton orbits backward. It travels in a highly inclined retrograde path, moving in the opposite direction of its host planet. Because of this backward orbit, astronomers know Triton didn't form alongside Neptune. Instead, it was an independent dwarf planet in the Kuiper Belt. As it drifted too close, Neptune's gravity snatched it from deep space, locking it into this retrograde trajectory. A capture event of this magnitude is catastrophic. When Triton arrived, its gravitational influence disrupted Neptune's original system of moons, sending them crashing together and creating a massive shockwave of icy debris. Triton's history frames the outer solar system as a region shaped by violent gravitational kidnappings. Neptune sits at the dark edge of our solar neighborhood, but its characteristics offer a window into the rest of the Milky Way. This data visualization categorizes the thousands of exoplanets astronomers have discovered orbiting other stars. The frequency of Neptune-sized worlds surpasses both Earth-sized rocky planets and the massive Jupiter-sized gas giants. Our local ice giant is the cosmic standard. By studying its boiling mantle, its supersonic winds, and its captured moons, astronomers can build accurate models for how weather and gravity operate on the most common type of planet in the universe. Despite Neptune serving as the standard for alien worlds, it remains the least explored planet orbiting our sun. It has been visited by a single space probe over 30 years ago. The planet discovered by a pen in 1846 provides the definitive blueprint for the rest of the universe. We often assume the planets operate like a permanent, perfectly balanced mechanical clock, but that precision is a facade. The modern solar system is actually full. Our planetary orbits are packed so tightly that the addition of a single new mass would trigger rapid, widespread orbital destabilization. We are already living on the very edge of dynamical chaos. This instability is defined by Lyapunov time. Because gravity is nonlinear, a measurement error of just 15 meters in Earth's current position compounds exponentially over millions of years. Within 100 million years, this mathematical sensitivity makes it physically impossible to predict Earth's exact location along its orbit. The primary driver of this uncertainty is Jupiter. Its massive gravitational field exerts a continuous, subtle torque on the inner planets, specifically on the orbit of Mercury. In 2009, Jacques Lescar used thousands of parallel supercomputer simulations to map out the possible futures of these gravitational interactions. The data revealed a 1% chance that Mercury enters a gravitational resonance with Jupiter. This interaction would pull Mercury's orbit into an extreme oval, forcing it to cross the paths of Venus and Earth. Once Mercury's path is distorted, it can destabilize the entire inner system. This could trigger a chain reaction of close gravitational encounters, leading to potential collisions between Earth, Venus, and Mars in about 3.3 billion years. Even if the planets avoid a kinetic impact, the physics of our star present a different threat. Over the next billion years, the Sun will brighten by 10%, eventually driving a moist greenhouse effect that will desiccate our oceans. Earth's biosphere has a non-negotiable expiration date, dictated by the invisible interplay of gravitational friction and solar radiation. 5 billion years from now, the Sun depletes its core hydrogen. This causes the outer stellar envelope to violently expand, transforming into a red giant. For the innermost planets, the end is certain. Mercury and Venus are hopelessly engulfed and vaporized by the expanding plasma. Earth's fate is decided by a physical tug-of-war. As the Sun sheds mass into space, its gravity weakens, pushing Earth's orbit outward. Simultaneously, tidal friction from the star's atmosphere drags the planet inward toward the fire. Recent ab initio tidal modeling indicates that the outward push wins. Earth escapes engulfment, migrating to a distant surviving orbit at roughly 1.5 astronomical units. But survival does not mean habitability. Earth endures only as a barren, irradiated rock, stripped of its atmosphere and everything that once lived there. As the Sun expands, the solar system's habitable zone, the region where liquid water can exist, is forcefully pushed away from the inner planets. This habitable zone becomes a temporary 370 million year band stretching deep into the outer solar system, bringing intense heat to the gas giants. On Jupiter's moon Europa, this energy triggers a rapid, asymmetrical melting of its impenetrable ice shell, turning the hidden ocean into a surface sea. Saturn's moon Titan shifts from a frozen world of liquid hydrocarbons into a temperate environment, potentially allowing liquid water to pool on its surface. For a fleeting cosmological window, the most hospitable real estate in our system will be the moons of the outer gas giants. Eventually, the Sun's outer layers drift away, revealing its final state, a white dwarf. This hyper-dense core emits a steady glow, but no solar wind. The surviving planets now orbit this tiny point of light in a perfectly quiet, stable, and profoundly freezing environment. This chart shows the Roche limit, a destruction radius surrounding the white dwarf. If a minor planet or asteroid crosses this threshold, the star's intense tidal forces exceed the object's internal gravity. Passing asteroids are violently shredded across this boundary, creating glittering rings of metallic debris that slowly pollute the atmosphere of the dead star. The only active process left in the entire solar system will be the silent grinding of ancient asteroids into cosmic dust. The outer moons freeze solid once again, and the surviving planets are locked in distant, dark orbits around a cooling remnant. This static graveyard stands in stark contrast to the chaotic, vibrant, and dangerous system we inhabit today. The solar system as we know it is not a permanent fixture of the universe. It is a fleeting chapter in an inescapable march towards stellar entropy.